All right, again, so here's chapter 2, section 3, part 1, graphs that enlighten. Some key concepts here in 2.3 will introduce graphs here that foster understanding of data. So again, as statisticians, we should be objective and non-biased, and we should carry those same principles through when we're creating graphs, as to foster understanding for our audience rather than deceive. In chapter 2, section 3, part 2, we'll discuss some graphs that are deceptive because they create impressions about data that are somehow misleading or wrong. And Excel is just one example of technology that provides us with powerful tools for generating a wide variety of graphs. For statistics, there's also some really specialized programs where you can make some really neat looking graphs. For those of you interested, Prism is one example of a really nice program that allows you to create graphs and figures. All right, now let's talk about graphs that enlighten. So one example here are dot plots. In dot plots, we have a graph of quantitative data in which each data value is plotted as a point or a dot. These dots are plotted above a horizontal scale of values. One important detail here is that dots representing equal values are stacked, and I'll show you an example of that. Features of a dot plot: it displays the shape of distribution of data. For instance, we see this shape here where there appears to be a lot of data at about 65. And here the data we're looking at is pulse rates of males. Another important feature of dot plots, it's usually possible to recreate the original list of data values. So one example here, if we see two dots stacked over 50, it means that we have two data points of the value 50. Back to this bullet point, as we see data displayed like this in a dot plot, if we can figure out the scale here, so 50 through 60, we have, this might be 52, 54, 56, 58, and then 60. So if we can tell what scale this is, we can recreate a list of all the data points that were used to make this dot plot. For example, 50, 50, 52, 52, 52, 52, and another 52. So we could look at this dot plot and recreate the list of values that was used to create this graph in the first place. Next, another interesting way to display data here is through a stem plot. You might also hear this called a stem and leaf plot. So stem plots represent quantitative data by separating each value into two parts: the stem, such as the leftmost digit, and the leaf, such as the rightmost digit. One note I want to say here, so quantitative, this is when we have actual quantities. We also have qualitative data, such as colors of shirts, things like that. So remember, quantitative data, we have a quantity to it, versus qualitative data, we do not. So let's look at creating the stem plot. Here we have 4, 0, and 2. That means we have pulse rates in our data set of 40 and 42. Okay, so on the stem portion, we displayed the leftmost digit. In the leaf portion here, we're displaying the rightmost digit of 0 and 2. Okay, so you would go on and make this stem plot based on your other sets of data. One detail here I want to point out is if we have 10 in our stem and 2 and 4 in our leaf, what data would that represent? So here the data values are 102 and 104. Okay, so interpreting and creating these stem plots, you have to be really careful about what's representing the stem and what's representing the leaf, and be really organized. Some features of a stem plot: again, stem plots show the shape of a distribution of data. So we can see here that because there's so many data points where the stem is 6, we have a lot of data values where the pulse rate is around 60 to 70. Another nice feature about stem plots, it retains the original data values. So we could most definitely look at this stem plot and recreate the list of data that was used to make the stem plot. For example, 40 and 42 are data points. One other feature here, the sample data are sorted, so they're arranged in order. For example, here we go from 4 to 10, so we have an increasing order of data values or pulse rates. Next, we have bar graphs, where a bar graph is a graph of bars of equal width to show frequencies of categories of categorical or qualitative data here versus quantitative. A note here with bar graphs, the bars may or may not be separated by small gaps. That does not indicate a gap in the data. Whereas for histograms, if we saw a gap in the bars, that indicated a gap in the data. But for bar graphs, that's not necessarily true. So you really have to look at the axes on your bar graphs to tell what's going on. For example, here we have gaps here between the bars. That does not indicate a gap in the data. And here we have another example of a bar chart where we have bars that are grouped together intentionally. Okay, so to understand what the gaps mean in the bar charts, you really do have to look at the axes on the graph to interpret what the data is showing. A feature of bar graphs, it shows the relative distribution of categorical data, again, qualitative, not quantitative, so that it's easier to compare the different categories. So here in this example, each of these is a separate category, and you're going to practice making a bar graph in your student outline. The example in your student outline is we have days of the week, 30 children were born. So to get you started, you may want to create a table like this, and this is not the same data that's in your notes. So a table like this. So you want to write out the days, you'll tally up the number of data points within each day, and then you'll get a total frequency corresponding to that day. Okay, so if this helps, you'll make a table like this, then you'll end up making a bar graph. On the y-axis, we have the frequency. So for example, from Monday, we would show a frequency of 5. And as you're making this bar graph, I want you to figure out what would be on the x-axis here. Next, and similarly, we have Pareto charts. A Pareto chart is a bar graph for categorical data, but we have the added stipulation that the bars are arranged in descending order according to frequencies. So because the bars decrease in height from left to right. So with Pareto charts, you can take a bar graph and easily convert that into a Pareto chart after you know the frequencies of each category. So then once you know the frequencies, you would arrange them in descending order so that the bars decrease in height from left to right. So you start out with the category with the highest frequency, and you end up with the category here that has the lowest frequency. Some features of Pareto charts. A Pareto chart shows the relative distribution of categorical data so that it is easier to compare the different categories. In comparing Pareto charts to bar charts, Pareto charts really accentuate the differences in frequencies between the different categories. So these charts can draw more attention to, quote, the important categories, whether the most important category is the one with the highest frequency, or perhaps the most important category is to know which has the lowest frequency. Okay, so next we have frequency polygons. A frequency polygon is a graph using line segments connected to points located directly above class midpoint values. So do you remember us talking about this for histograms? These frequency polygons are very similar to a histogram, but a frequency polygon uses line segments instead of bars. Now I know you remember this, but let me refresh you on the meaning of a class midpoint value. If you recall from our lecture on histograms, class midpoints, these are the values in the middle of the classes, where each class midpoint can be found by adding the lower class limit to the upper class limit and dividing that sum by 2. So again, going back to our histogram section, we're going to add our lower class limit of 75 plus our upper class limit here of 124 and divide that by 2 to get a class midpoint of 99.5. To find our other class midpoints, we would repeat that for each of these classes or categories. Now let's see that in a frequency polygon. Okay, so previously we calculated that one class midpoint is 99.5. So we see a point or a dot located directly over that class midpoint. Then on the y-axis, that class midpoint dot corresponds with 11. So it corresponds with the frequency of that class. Now, maybe on your own, you can figure out where we got 49.5. So pause the video and try to figure out where we get 49.5 from. So to get this class midpoint of 49.5, we would take this lower class limit, subtract the class width, and again, go back to our section on histograms to remind yourself of the class width. Here the class width was 50, so we take 75 minus 50, that's equal to 25. So although we don't have any data in that class, we can make a theoretical class to figure out this class midpoint. So for this extra class up here, we have a lower class limit of 25. What would be our upper class limit? To find that upper class limit, we take 75 minus 1, which is 74. So this theoretical class up here would go from 25 to 74. And again, we don't have any data in that class, but that's how we can figure out the class midpoint. So we take 25 plus 74, divide that by 2, and that's where we get 49.5. Okay, so practice doing this here again for this other class midpoint of 349.5. See if you can figure out where we got that value. Okay, and remember, frequency polygons are really similar to histograms. So just as we saw in histograms, we can also have relative frequency polygons. So a variation of the basic frequency polygon is the relative frequency polygon, which uses relative frequencies, so either in proportions or percentages for the vertical scale. Now again, we touched on this in the histogram section. To find the relative frequency for a class, we'll take the frequency for that one class divided by the sum of all the frequencies in that set of data. To then get percentage for a class, we'd take that same value here and multiply by 100 to get the number into a percentage. Okay, so here's an example of a relative frequency polygon. In the histogram lecture, we took 11 divided by the sum of all these frequencies, which is equal to 50. So we take 11 divided by 50, and we get 0.22. Then to go from 0.22, so what we've done here, into a percentage, we multiply that by 100 to get 22%. So where do we see that in the relative frequency polygon here? We have our class midpoint of 99.5. Then we have percent here on the y-axis. So this data point does line up with 22%. Okay, and on your own, I recommend practicing to figure out where these data points come from. One note here, this graph shows both the relative frequency polygon style, where we have a relative value here on the y-axis, so percent or proportion. This style is also an example of comparisons, which we did cover in the histogram lecture as well. So in comparisons, we're putting two different sets of data and displaying them on the same graph, which we also practice doing for histograms using both Dunkin' Donuts and McDonald's. Next, we have pie charts. This is a very common graph that depicts categorical data as slices of a circle in which the size of each slice is proportional to the frequency count for the category. And here the slices of the pie should add up to about 100%. One feature of a pie chart, it shows the distribution of categorical data. Okay, so again, categorical / qualitative data. This is as opposed to quantitative data. So this shows the distribution of categorical data in a commonly used format that is usually pretty audience friendly. So here, for example, a pie chart of stolen boats or watercrafts. It's evident that jet skis appear to be stolen the most frequently, then motorboats, and so on, with evidence here that sailboats are stolen the least frequently. Next, we have a time series graph. So a graph of time series data, which are quantitative now, that have been collected at different points in time, such as monthly or yearly. So a feature of time series graphs, it reveals information about trends over time. So here's an example. We can plot years on the x-axis. So we go from 1985. Our next tick mark here on the x-axis is 1990, so 5 years later, so on and so forth. Okay, so that's the end of covering graphs that enlighten. So this is chapter 2, section 3, part 1, and the next part will cover graphs that deceive. Okay, so I hope you're all doing well. You're feeling more comfortable with this material. Always reach out if you have any questions. And I'll see you next time for part 2, so graphs that deceive. All right, now, so we're continuing on chapter 2, section 3. This is part 2, so graphs that deceive. So now we're here in the chapter 2 outline. One way that graphs can deceive is using a non-zero vertical axis. So a common deceptive graph involves using a vertical scale that starts at some value greater than 0 to exaggerate the differences between groups. Let's look at an example. So here on the vertical scale, we have percent of patients experiencing nausea when they've either taken a painkiller like Oxycontin or a placebo. Now for Oxycontin, it looks like the percentage of patients experiencing nausea is about 23%. For the placebo, so remember this is a sugar pill, it might be about 11%. But notice here the graph on the left, we start at 10% on the vertical axis or the y-axis, and then our range of values only goes up to 24%. Whereas here on the right, we start at 0% and we go up to 25%. So looking at this graph on the left, how this data is displayed, it looks like the percent of patients experiencing nausea is way greater than the patients experiencing nausea who have taken the placebo. Versus this graph on the right, we do still see this difference, but it's not nearly as exaggerated. So again, looking at these graphs, pay close attention to where we start our y-axis or our vertical axis. Another way graphs can deceive is by use of pictographs. So drawings of objects called pictographs are often misleading. Let's see why. Data that are one-dimensional in nature, such as budget amounts or numbers, may be depicted with two-dimensional objects, such as dollar bills, or even three-dimensional objects, such as stacks of coins, homes, or barrels. One note here, if the images are represented as three-dimensional, the misleading effect is even greater than if they were two-dimensional. Now let me provide you with some further context of pictographs. So by using pictographs, artists can create false impressions that grossly distort differences by using these principles of geometry. For example, when you double each side of a square, the area doesn't merely double, it increases by a factor of 4. So let's visualize this. We know that area is equal to the length of the side squared. So for this first square, we have lengths of 1. So when we square 1, our area here is still 1. Now if we double each length of the square, each side is 2. If we square 2, our area becomes 4. So what we're getting at here, if we change a shape slightly, so we double these sides, we can actually make a big impact by how the overall area is visualized or presented to us. Another example geometrically, when you double each side of a cube, its volume doesn't merely double, it increases by a factor of 8. So we know the formula for volume, it's the length of a side cubed. Here each length is 1. When we cube 1, that volume is still 1. If we double each side here to 2, and then we cube 2, our volume is 8. So this increased by a factor of 8. So again here, seemingly small changes geometrically can actually make a pretty large impact visually. Now let's look at an example with data. So here we're looking at percentages of adults that smoke, and again values, data, percentages, this is all one-dimensional data. When we use pictographs, however, we're adding two-dimensionality or three-dimensionality to our data. So in 1970, 37% of US adults smoked. In 2013, that number reduced to 18%. Now again, taking these numbers of 37% versus 18%, our percentage decreased by about half. Yet when we represent this data using pictures of cigarettes, the statisticians here, or the artists who made these images, are sort of deceptively displaying 37% versus 18% by showing a very large cigarette versus a smaller cigarette. So again, these pictures don't really tell us numbers, they're making an impression on us visually. So these pictographs are just one way that data can be displayed deceptively. Another way that graphs can deceive is by manipulating the axes. So the scale of the y-axis can be compressed or stretched to manipulate the appearance of the data. So here for this example, we start at 3.140% and we go up to 3.154%. So we've really zoomed in on a really small window of percentages here. Versus in this example on the right, we start at 0.00%, we go up to 3.50%, and we still show data from the same years here, so 2008 through 2012. But comparing these two graphs, they leave an impression that's very different from one another. So here on the left, we think there's a large increase between 2008 and 2012, but really we're only increasing here from about 3.141 to 3.152. And here on the right, we're showing that these interest rates are almost equivalent to one another over these years, but it's really important to consider what data we're actually looking at. So maybe this increase in interest rate from 3.141 up to 3.152% is actually significant. So again, we need to really critically think about the nature of the data that we're displaying. And now you may have seen this before. So here horizontally, we have our x-axes, and here vertically, we have our y-axes. Okay, so that's something important to know as we move forward. Another point here, the difference between the tick marks can even be changed to stretch or compress certain parts of the graph. So the tick marks used here are boxed in purple. So we have a tick mark at 0.00, 0.50 for the graph on the right. But for the graph on the left, our tick marks are 3.140 up to 3.142. So those tick marks are spaced very differently compared to the graph on the right. And here's another image displaying this definition of tick marks. So here on our y-axis, our vertical axis, our tick marks are between 0 to 20 to 40 to 60, etc. On our x-axis, we're showing tick marks between the year 2010 to 2011, and so on. Another example here, you can see on the y-axis that symbol and in these bars. So that means that there's a break in the y-axis and they're leaving out the data points between about 300, 400 up through about 1900. So all of those values are just missing from the graph. So while the red S gene might not look to be too much greater activity-wise than the PAC gene, the red S gene is actually above 3000, while the PAC gene is just a little bit below 300. So you have to watch out for those symbols as well. Here's another example of manipulating the axes. So here for both the y-axis and the x-axis, again, this is the y-axis, this is the x-axis. We have a scale that goes from 1 to 10 to 100 to 1000, and again, the same on the x-axis. This is an FYI, this is called a logarithmic scale. Now again, this just shows we really need to pay attention to our axes and our scales here, because this could appear linear if we did not look at what these numbers actually are. Where linear data, for example, is having steps from 0 to 10 to 20 to 30 to 40 to 50, etc. But for logarithmic, we jump from 1 to 10 to 100 to 1000. Now here's another example to look at. So for graph 1, we have millions of US dollars on our y-axis going from 0 to 25. And on our x-axis here, we start with 1987 up through 2007. And each value here on the x-axis is separated by 1 year. So we have 1987 to 1988, etc. However, for graph number 2 here, this is the same data, yet we've lumped in 1987 through 1989, 1990 through 1991, yet here in 1996, that's its own data point. So this x-axis has definitely been manipulated to show the data in a different way. Again, here with graph number 3, this is all the same data. We have 1987 to 1988, so we're going in 1 year increments here. Yet at the end, we have 2004 through 2007 all lumped together. So all these graphs show a different scale on the x-axis, yet only the first graph really effectively displays the pattern of change through time, while graphs 2 and 3 seem intentionally deceptive. Next, we have this concept of cherry picking the data. And cherry picking is defined as the action or practice of choosing and taking only the most beneficial option from what's available. But remember, for us as statisticians, we're going to be non-biased and we will not do things like cherry pick the data. So here are 2 different representations of the same data, yet they tell very different stories. In this case, we look at both axes and they've been manipulated. So here on the y-axis, we go from 55 to 56, 57, 58, 59, 60. So we've zoomed in between 55 and 60. Yet here on the y-axis, we go from 0 to 4,000. And then on the x-axis, we go from 1900 up to 2000. For this graph on the right, we're displaying the same years, but the scale here and the tick marks are very different. So which graph is better? Actually, neither of the graphs are that enlightening to look at. For the graph on the right, all of this empty space really isn't beneficial to the viewer. For the graph on the left, though, we're so zoomed in that we also don't really get a clear impression of what the data is showing us. Next, we have using the wrong type of graph. So for example, if respondents were asked if they like each brand A, B, and C, 70% of the sample enjoys using brand A, 65% of the same sample enjoys using brand B, and 60% of that same sample enjoys using brand C. Now here, if we're displaying the data like this in a pie chart, this is absolutely not the correct way to show this data. For one, these percentages add up to way more than 100%. And also we have to remember why we use pie charts. So we use these to show parts of a whole. But in this case, 70% of the respondents said they enjoy using brand A, but that didn't make an impression on whether or not they said they also enjoy using brand B and brand C. So we should not be lumping this data all into one pie chart. And importantly, again, pie chart should add up very close to 100%. So there's a lot of things wrong with displaying the data like this in a pie chart. And maybe for fun, think about how you might display this data here. I think I'd probably use a bar chart. Next, we have going against convention. So this frequently involves the use of color. Usually the darker color, the more of something there is. And for the lighter color, the less there is. So switching this convention can be misleading. Here's an example. So again, usually for darker colors, the more of that there is, and for lighter colors, the less. But here, if it's intuitive to think that the darker means more of that thing and the lighter color means the less of that thing, we might look at this representation on the left and assume that because Alaska looks darker, then we have the most individuals per kilometer. Okay, so here it's best to go with our typical convention. One other notion to keep in mind with using colors is that some amount of the population experiences color blindness. So it wouldn't be good, for example, to include this side of the scale being red and this side of the scale being green, because that would look all the same to an individual with color blindness when they can't tell the difference between green and red. Okay, so again, this one would be more intuitive to look at, whereas this one is more misleading. Next, this is somewhat similar to what we've already talked about here, and we have the category of no scale. So by not having tick marks at regular, evenly spaced intervals, the appearance of the data can be altered. And again, we sort of touched on this. So here on the right, 120 up to 150, that's a 30-unit difference between these tick marks. And it's really unclear if this is 0 and then we go up to 120, and the y-axis only covers this amount of space, and now we're going from 120 to 150, and it's covering this amount of space. Whereas on the left, it's a little bit better. We're assuming this to be 0. We should include marks here, so we could say 30, 60, 90, 120, 150. So again, this one on the left is a little bit better, but it's still not ideal. So remember, on both axes, we need to clearly mark the tick intervals. They could be set to 5, 10, 30, etc. When using bar graphs on the x-axis, usually these are pretty clearly denoted. But for graphs other than bar graphs, where we have an x-axis with numbers, for example, we would want to clearly mark the intervals for something like that. And here for this second example, the difference between A and B is much more exaggerated than it is here. Okay, lastly, we don't want to overload the graph with information, especially information that shouldn't be linked together in the first place. So here we have these two data sets, the first being the number of individuals drowned. Again, drowning is not my favorite example to use, but here it is. The second set of data, we have the number of films that Nicolas Cage has appeared in. So I think it's pretty clear we should not be putting these two different data sets together in one plot. And it makes it really difficult for the reader to know what to look at. This is an FYI, the creator here has made use of dual x and y axes, where here on this left y-axis we have 80, 100, 120, 140 drownings, and here on the right y-axis we have 0, 2, 4, and 6 films. I guess one thing this graph has going for it is that at least the x-axes are the same. But still, this is not an example of a graph that you would want to create or look at. It's really oddly deceptive to put these two different sets of data together on the same plot. And I'll leave you with that. So to finish up, some additional notes here for 2.3. It's sort of fun to think about this. So in addition to all the graphs you've seen here in this section, there are plenty of other useful graphs we didn't cover, and even ones that may not have been developed yet. So it's sort of fun to think in statistics that there could be other graphs that we eventually develop in the future. And that's where future statisticians like maybe you come in. Remember, the ultimate goal of graphs is to enlighten the audience rather than deceive the audience about the nature of the data. One more additional note, there's a lot of variation that can happen in the visual display of quantitative information. And remember what our definition of quantitative here is, so using actual quantities. An American statistician, Edward Tufte, offers these principles. The first is for smaller data sets of 20 values or fewer, using a table instead of a graph is usually ideal. So remember what tables we've talked about now? They're called the frequency distribution tables. Next, a graph of data should make us focus on the true nature of the data, as stated before, not on the other elements, such as eye-catching but distracting design features. Similarly, do not distort the data intentionally. Construct a graph to reveal the true nature of the data. Overall, be as non-biased of a statistician as you can be. One additional principle, almost all of the ink in a graph should be used for the data and not on other design elements. So really keep the graphs clean and clear for your audience to interpret. Okay, that is the end of both parts of Chapter 2, Section 3. Have an excellent day, and talk to you soon for Section 4.